In this video, we're going to talk about linear equations, which is one of the most central problems in linear algebra. The central problem of linear algebra is to solve a system of equations, and those equations are linear, which means that the unknowns are only multiplied by numbers. So these linear equations are actually quite simple. So we're talking about linear equations. And for example, let's take this system of linear equations. X minus 2y equals to 1, and 3x plus 2y is equal to 11. So this is a simultaneous equation with two equations and two unknowns. Now, in linear algebra, we're no longer just trying to solve these equations. We're trying to interpret them, maybe geometrically or maybe algebraically. But we have to do so using a different approach. So let's first look at something I call the row picture. And as you heard, it's a way of imagining what's happening in this system of linear equations. So we begin a row at a time. Now, what's a row? A row is simply this equation, right? So the first equation, x minus 2y equals to 1. Let's look at this in isolation. This equation describes a straight line in the xy plane. Now, it also, you can say it describes the point xy in R2 such that this equation is satisfied, so a locus of points. The slope of this particular line is, let's write just slope, is a half. And that gives us a particular line on the xy graph. So let's plot this straight line. So we see that this straight line goes somewhere over here. Nice. And this point is 1 because 1, 0 is a point. And nice. That's a very sketchy plot, but that'll do for the time. Now, the second row, or you can say the second equation, is described by 3x plus 2y is equal to 11. This describes another line. Now, the slope of this line is negative 3 over 2. And because the slopes aren't the same, which means that the lines aren't parallel, we can say that the lines will meet at a point. Now let's plot this particular equation too. It simply crosses the line like over here. And so this is the intersection point. Now how do we find the intersection point from the row picture? Well, it's simple. You simply look at these two equations and try to solve for them. What you can do is you can isolate y and then get an expression in terms of only x's. And so the y's for row 1 and row 2 has to equal, and thus you can solve for the x and thus the y. Now, let's quickly solve for this, okay? So we have this particular equation. Let's duplicate this. And let's simply say, let's add row 1 plus row 2. Now this produces 4x is equal to 12, which implies that x is equal to 3. Now this also implies that y is equal to x over 1 over 2 from equation 1, which means that y is equal to 3 minus 1 over 2, which is 2 over 2, which is 1. Nice. We have successfully found the point of intersection, which is also the solution to this particular system of equations. So let's write this out. The solution is 3, 1, which is xy. So from the row picture, we see that the row picture reveals two lines meeting at a single point. And notice that the row picture shows us whether we will have a solution. If the slopes of these two lines are the same, then we have two cases. Either these two lines are the same line, in which their intersection point will be this line, or the two lines are parallel but are not the same line, and thus there will be no meeting solution. So we have three cases. Either they will meet at a line, or they will never meet. So this is pretty useful because it tells us that we cannot have, two intersection points, at least not in the Euclidean plane. Now let's turn to the column picture, because you probably have seen the row picture in middle school or high school when you're trying to solve for simultaneous equations. Your teacher probably have told you that the rows describes lines and that the solution is the intersection of these two lines. But the column picture is really where linear algebra comes in. The column picture. The column picture is the picture that you'll be using mostly in linear algebra. We're going to treat this system of equations as a matrix equation, and we'll be deriving that very soon. So first of all, let's look at how we can turn this equation into vectors. Notice that this equation can be written like this. X times vector 1, 3 plus y times vector negative 2, 2 plus 1, 11. Now notice that if we expand this, all we get is x minus 2y, 3x plus 2y. This particular vector is equal to 111. And let's call this vector b. So this is simply a compact form of what we have above over here. Nice. And so let's look at this for a second. Notice that this is a linear combination of vectors. X and y are variables that we want to find. They're basically constants, real number constants. And there's two column vectors. So the problem now is to find the combination of those vectors that equals the vector on the right-hand side, namely b. We're multiplying the first column by x and the second column by y by adding, and this is a linear combination. So we have successfully transformed our row approach, or the row picture, to an interpretation of column vectors. So we're no longer looking at the rows, but instead at the columns. And that's why we call it the column picture. So let's graphically look at this. Let's graphically look at what's going on. So we have two vectors, and we're trying to combine them to give 111. So where's 111? Probably over here. Where's 13? 13 is probably like over here. And where's negative 2, 2? We can say it's over here. Well, this is just a very roughy sketch, so please don't mind. This is 13. Now, we have already found the solution, so let's verify that solution in the column picture. So our solution is 31xy. This means that our x over here has to be 3. And so we multiply this particular vector by 3, which is probably over here. And our y is 1, which means that we multiply negative 2, 2 by 1. So we can join them head to tail, which is this vector is equal to negative 2, 2, and this vector is 3, 9, after we multiplied vector 1, 3 by 3. And sorry about this because this is very not to scale, but you get the idea. I'm trying to show you that the right-hand side vector b is simply a combination of the column vectors we derived from our system of equations. Now, some people prefer the row method and some people prefer the column method. Both of these methods are good, but when you go to higher dimensions, like 4 dimensions or n dimensions, you notice that you can't really imagine how, for example, in 4D hyperplanes will cross with each other. It's hard to imagine that, or merely impossible to imagine such a thing. And so it's much more convenient to imagine vectors linearly combining to form the right-hand side vector b. Okay, now we have a vector equation, a linear combination of vectors yielding a solution vector, yielding a right-hand side vector. We can write this, as we've seen in our previous videos, as a matrix vector equation. Our coefficient matrix, which is a name that you might want to remember. So a coefficient matrix. We define this as A, or you can call it any name you want, being the column vectors stored in this matrix. So we have 1, 3, negative 2, 2. So this is column 1 and this is column 2. And we call these vectors the column vectors, or the columns of matrix A. Well, that's pretty intuitive. And this is very typical of linear algebra, to look at a matrix by rows and columns. The rows give the row picture, and the columns give the column picture. Well, they give us the same numbers, or the same solutions, different pictures, and the same equations. we write those equations as a matrix problem. So we can write this now as ax equal to b. Expanding this, we have 1, 3, negative 2, 2 times vector x, which are the unknowns. Don't confuse this x with the x we used above. And we have the right-hand side vector b, 111. Now, we have successfully written this in terms of the matrix equation. We call this the matrix equation. And in fact, this particular form will be governing your linear algebra course. That's enough for 2D space. Let's consider 3D. So let's consider 3 equations and 3 unknowns. Now, the 3 unknowns we have are x, y, z. Let's just call it that. And let's consider the linear equation. X plus 2y plus 3z equals to 6. Sorry about that, 3. 2x plus 5y plus 2z equals to 4. And 6x minus 3y plus z is equal to 2. Nice. This is a very particular 3 equation and 3 unknown linear equations. Now, we're trying to look for the numbers x, y, z that solve all the 3 equations at once. Those desired numbers, as we said above in the 2D case, don't always exist. And notice that in the row picture. Let's consider the row picture first. Now, notice that these 3 equations simultaneously describe 3 planes, and we're trying to find the intersection point of these 3 planes, given that they exist. Well, they might not exist if there are 3 parallel, non-equal planes. So the row picture tells us that 3 planes intersect at, we have nowhere, which is one option, 1 point, which is when the 3 planes aren't parallel at all, and at a line, in which we have 2 planes intersecting a line, and the third plane is the same as plane 1 or plane 2. Or they could intersect at a plane, which means that the 3 planes are equal, so they are the same plane. Now the column picture is where things get really interesting. Now, there's a reason why we didn't use the row picture to solve for these 3 equations simultaneously. The reason is it's very hard to solve right now because it's very hard to see how we can, manipulate these 3 equations, subtract them or add them from one another to get or isolate an x or an y or a z. What we can see from the column picture, if we put them into columns, is we have x, 1, 2, 6, plus y, 2, 5, negative 3, plus 3, 2, 1, times c. That's equal to the right-hand side vector, 6, 4, 2. Now notice that for the third term, we can simply multiply this third vector by 2 to get this vector. And so, yeah, we have found the solution. The solution is when z is equal to 2 and when x and y are equal to 0. And thus we have solved this system of equations. Nice. Now, it's not always going to be very easy to see from the columns how they will combine to give this. But my point is that if you look at this in terms of only the rows, then it will be very hard to solve this problem. But if you also look at it in the column picture, there might be a way to solve this in a more easy way. And so if you want to look at this in the column picture, we have our 3 vectors. And because the 3 planes I've given are pretty nice, so they aren't parallel to one another, they intersect at a point. And so our 3 vectors are what you will learn to see are independent. And so they will span the whole 3D space. And therefore, their linear combination is going to span R3. And since the linear combination spans R3, that means for any vector, right-hand side vector b, then a combination of the 3 vectors will always give that vector. So we can always find a linear combination such that they combine to form the right-hand side vector. Okay, nice. We're not going to look at 4 dimensions because you can probably extend this yourself by looking at how we can combine columns or by looking at how the rows interact with one another. Now, let's look at matrix multiplication in terms of the row picture and column picture. Namely, let's look at how we can use the row picture or the column picture to look at how we can interpret matrix multiplication with the vector. So let's look at this. Consider our previous coefficient matrix from this equation. We haven't actually derived it, but it's easy to see that the coefficient matrix simply stores all the coefficients in front of the unknowns. So I'm simply going to write this out. The matrix equation AX equals to B is 1, 2, 3, 2, 5, 2, and 6, negative 3, 1. This times the vector of unknowns, x, y, z, that's equal to 6, 4, 2. Now, what does it mean to multiply A times vector x? We can multiply by rows or by columns. It's very similar to our row picture and the column picture. And either way, AX equals to B must be a correct representation of the 3 equations. So let's look at how we can multiply by rows and by columns. So, row picture. Now notice that we can write this equation as 1, 2, 3, the vector, dotted with the vector x, y, z. Nice. We can also do the same for the other rows. And that's equal to the right-hand side vector, 6, 4, 2. Nice. So that's a nice interpretation of matrix multiplication, a series of dot products. And notice that in total, there are 9 individual products, right? Even though this is a dot product, which is one individual product, what we have is one product over here, one product over here, and one product over here. And in total, there's 3 times 3 equals to 9 products. And therefore, we can extend this to matrix of any sizes. AX, we can write this as, well, we have m rows, let's say. That's equal to row times this particular vector, which can also be written as row 1 dotted with x, all the way to row m dotted with x. So there's this very nice simplicity to the row picture. Now let's look at multiplication by columns. So the column picture of matrix multiplication. So the column picture tells us that we can treat a matrix times a vector as a linear combination of the matrix columns. What we can write is AX is equal to x1 times column 1, so col 1, all the way to, let's say there's n columns, all the way to xn times column n, so a linear combination of the columns. Nice. In this particular tutorial of linear algebra, we're going to be focusing on the column picture, but notice that the row picture is also very useful. And in fact, elimination, we will learn in the next series of sections, actually uses the row picture. So combining these 2 approaches will make your life much more easier. So let's look at 2 examples. So for example, let's consider the multiplication AX, which is equal to 1, 1, 1, 0, 0, 0, 0, 0, 0. And 4, 5, 6. Now, try to do this yourself. Try to use the row picture and the column picture, or the 2 different approaches in matrix multiplication. In this example, both of the methods are pretty easy, and notice that the answer is 4, 4, 4. Now, let's consider another matrix, and I'll call this matrix I for a reason we'll see later. So I times x is equal to 1, 0, 0, 0, 1, 0, and 0, 0, 1. And we can multiply this by 4, 5, 6. Now, what is the right-hand side vector over here? The correct answer is 4, 5, 6. Well, notice that these 2 vectors are the same. And actually, we can prove this. Well, notice that I times x, where x is any arbitrary vector, so we'll actually write this in the general form. If we multiply this by any arbitrary vector, This, you can use the row picture or the column picture. Well, if we use the row picture, then we have this vector dotted with x, y, z, which is x, and then we have y and then z. It's pretty easy to prove this yourself. Now, notice that I is kind of like the number 1 in normal arithmetic. We call it the identity matrix. And it's a very useful matrix that we'll see. It defines what an inverse of a matrix is, and it also exhibits this very nice identity property, which is very analogous to our algebra. Now, that's it for this video, and let's summarize what we've learned. So we learned about how we can use the row picture or the column picture to interpret systems of equations and matrix multiplication. And in fact, we also told how we can relate the system of equations to matrix multiplication. We can convert a particular system of equations to ax equals to b. Now, this conversion is very important, and we'll be doing it very often such that you'll not even notice that you're using the concepts of this tutorial. And that's it for this video. For our next section, we'll be talking about elimination, which is a very systematic way to solve for linear equations. And in fact, using a computer, it's very convenient to solve any system of equations. So, thank you for watching this video, and see you in the next.